Hello guys, we are presenting a project on manipulation of audio signal. Now let's start. Fs equals 44100. Here Fs represents the sampling frequency. Our audio signal is going to be sampled at this sampling frequency. Now y equals audio rate. Audio rate. Here we are importing our audio file. In order to import it, click here, go to music, select folder. Here these are some of the musics in our music folder. Now we are selecting this dsp.mp3. double click here like this, go to finish, click OK. Here we have imported our audio file. The name is dsp.mp3. Here audio read function read our audio file and is being assigned to the variable y. P equals audio player y fs. Here we are using this function audio player in order to sample our audio signal y to this sampling frequency, and the sampled audio signal is being assigned to the variable p. Now let's play our audio signal and see. Play p.
Missy all the cutie girls standing up in the corner. Get up in the dance hall tonight.
This is our audio signal. This is how it plays. Now coming to the part of adding noise, removing noise, creating echo. First, adding noise to the audio signal. Here we are adding an additive white Gaussian noise x equal. We are using function awgn of y comma fs y comma 10. Here awgn is a function. Here it means additive white Gaussian noise. This is our original signal and this is the signal to noise ratio. That means that if we are adding more noise, this ratio is small. If we are adding less noise, this ratio is more. So in order to add more noise, we should make this ratio as small as possible, and that now x represents the sound with noise, that is after adding noise. Now let's play the sound with noise, whether let's see whether the noise is associated with the sound or not. Sound of x fs. Now you see that the noise is associated with the sound. Now we are going to remove this noise. For this we are using a low pass filter. For that LP low pass filter equals f design dot low pass fp comma fst comma ap comma ast 3000 comma 2500 comma 0.5 comma 50 comma fs. Here we use this function f design dot low pass in order to design the low pass filter. Here fp represents the passband frequency, fst represents the stopband frequency, ap for passband attenuation, ast for stopband attenuation. These are the corresponding values for fp, fst, ap, ast, and this fs is our sampling frequency. D equals designed HLPF. Here we are designing the low pass filter using this function designed, and that filter is represented by the variable D. Now we are going to filter the noise using this function is equals filter D comma X. Here this filter function filters the noise using this filter D, and that filtered audio signal is represented by the variable S. Now let's see whether some noise has been filtered or not by playing the sound. After filtering, sound is comma FS. Now you see the intensity of the noise has been reduced. That means noise has been removed, but some noise is still associated with the sound, because in case of erythroid Gaussian noise we cannot completely remove the noise. If we are going to completely remove the noise, then the audio signal will be gone completely. So in order to differentiate how much noise has been removed, we'll plot graphs of original sound with noise, and the sound after filtering. We'll plot like this: subplot 3, 1, 1. Oh, it's coming now. Plot. Okay, plot Y, then subplot 3, 1, 2, then plot X, then subplot 3, 1, 3, plot S. Now you will see this is the graph for the original song, that is without any noise. This is the graph of the sound after adding noise. This is the graph of the sound after filtering the noise. Here you see some more blue colors. This represents the noise, and here still you're getting some blue colors. This is the noise that is associated with the sound after filtering. Here you see the original. In case of original sound, the graph it is varying from minus 0.25 to 0.25. In case of sound after adding noise, it's varying from minus 1 to 1, around like that. And in case of sound after filtering, it is varying from minus 0.5 to plus 0.5, like this. But original sound and the sound after filtering, they're almost close to each other. That means that some part of the noise has been removed. Now coming to creating echo in the audio signal. Stereo mix now. Stereo mix equals Y. Here we are creating an array that is same as the old one. Now we have two audio files. We are playing these two audio signals with some delay in between them. That delay is given by kfn. There is the half of the sampling frequency, like this. For this we are creating a for loop from n equals n plus 1 to the whole length of original signal Y. Stereo mix of n comma 1 equals Y of n comma 1 plus Y of n minus cap n 2. Then stereo mix n comma 2 equals y of n comma 2 plus y of n minus cap n comma 1. This is the end of the loop. Here stereo mix, this part is for creating echo from right to left, and this part is for creating echo from left to right, and this is the end of the loop. Now let's see, let's play the sound and see whether echo is coming or not. Like this sound, stereo mix, comma fs. See, now you have seen that echo comes, right? So like this, we can manipulate any audio signal in different ways. For example, if we want to reduce or remove some part of the audio signal, we can use the following code like this. Left equals y of comma 1, y right equals y of comma 2, y left minus y right equals y left minus y right. Now this is y left represents the left part of the sound in the graph, y right represents the right part of the right side of the sound in the graph, and here we are removing some part of the left part of the sound in the graph, and we are removing here some right part of the sound, and this is the, we are subtracting y right from y left. And now let's see whether the sound has been reduced or removed some part. Let's play and see. Sound y left minus y right my fs Now you have seen that some part of the audio signal has been reduced or removed. Now that's all for our project. Thank you.